Alright guys, so this is your first practice packet exam. So all I did was I went through the 2017 final exam given to actual students. I cut out all the stuff that I know we have never learned, and I just made it into a mini packet that you can do. So it's all over here, and I'm just gonna work it out. So I would highly suggest you actually try to practice it. And then look at this only if you don't remember some of the older concepts from, let's say, exam 1 or exam 2, or just to figure out like what the answers are or how to do the answers. Okay, we're gonna dive right into it. The very first question is asking us to draw condensed Lewis structures, including all hydrogens and lone pairs of 5 non-cyclic isomers of C3H5N that have the skeleton structures shown in the template. Okay, none of the structures you draw should have charges. Okay, very specific. So to do this question, the first thing you have to realize is it's not asking us for contributing structures, and it's actually asking us for isomers. So whenever we work with isomers, you have to remember that you can move all the bonds and stuff around. So another thing to look for is, this is my formula. So we can figure out the total number of electrons I should have. There's 3 carbons, so carbon has a valence electron of 4, and 3 would give me 8, 9, 10, 11, 12, plus 5 from my hydrogen, plus another 5 from my nitrogen. So I get 22. I should have no more than 22 electrons. If you have more than that, something's wrong. Another way you can think of how many bonds or triple bonds or double bonds I have is using the degrees of hydrogenation, hydrogen deficiency formula, which was just 2H, that was 2 times the carbons plus 2 minus H minus any X's plus any nitrogens, all divided by 2. So if we put that formula into what we have, we get 2 times 3 plus 2 minus the 5 hydrogens plus the 1 nitrogen, all divided by 2, and I get 3 times 2 is 6, 7, 8, 9, 9 minus 5, I get 4, 4 divided by 2 gives me 2. So if you remember, the degrees of unsaturation was, if you have 0, you have to be alkanes. If it's 1, it can be a double bond or acyclic. If it's 2, then it can be 2 double bonds or 2 cyclics, or a double bond and acyclic, or a triple bond. So right off the bat, when I look at this question, I would want to start off with this thing. I know there's a CN there, and I know that's a functional group, so we can just make that C triple bond N, just like that. And then at this point, I'm missing 5 hydrogens, which works out perfectly for me because I can put 3 over there and 2 over here. So something like that. Nothing has charges, and if we want to make sure that we have 22 electrons, we can check that too. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. So we do indeed have 22 electrons, or valence electrons, so we were right from both ways. So another thing we could do is we can just make a triple bond wherever we want. We can, let's say, make a triple bond over here. You can even make one in the middle, it doesn't really matter. So let's say we make a triple bond over here. Well, then I will have an H over here because carbon has 4 things. You will have 2 H's here, and then you would have 1, 2 H's here with a lone pair, just like that. This is also going to have 22 electrons. We can also make the triple bond in the middle. This is how our degrees of unsaturation formula helps us, because I know you can't have more than a triple bond, so everything else should match up. So let's add 3 H's here. We'll add the other 2 over here because we formed the NH2 like that. So since I can't put my triple bond anywhere now, I have to go down to the next thing, which is double bonds and cyclic structures. But they specifically said you have to make non-cyclic isomers. So all I can do is double bonds. And 2 degrees of unsaturation, that means I can do 2 double bonds. So I can, again, make those anywhere. So let's make one with this carbon, and we can make another one with this carbon. and then we fill in the H's. Now this carbon has 4, this one needs 1 more, and this one needs 2, like that. We have total of 5. This one again will have 22 electrons. We could do another. We could do a double bond here, and we could do a double bond over here. So fill in the H's. This will have 1 more H. This one gets 1 H. This one gets 1 H, and this one gets 2 H's. And that's 5 H's too. And one of the last ones that's not even listed here, but if you want to make it, you can make it. That would be 2 double bonds over here. You would make 1 more H on the nitrogen. You would get 1 H over here, and then you would get 3 H's on this carbon. That would be an answer also. So if you made any of those, you're good to go. Just remember to do your degrees of unsaturation or do the total number of electrons and you should be fine. I think the degrees of unsaturation is easier personally. Okay, part 2 of the question, we have the same formula now, except now they say that everything has an octet, but the molecules should have formal charges. Okay, so I mean, not much is changing. We just have to have formal charges in this one. So going about this one, let's say if I have to have a formal charge, and you can't have NH bonds, which is the big thing. So if I want to put my H's, let's just put 3 H's here. Then I have 2 more left. So let's say I put one. I know I can't put H's in the middle here. So let's say I put like a triple bond here. Well, that gets a positive. And then we can put the last 2 H's over here. And this can be your negative. So now you have formal charges, but overall there's no charge. I know the overall thing shouldn't have had charge because then this thing, our formula should have had a charge. So that's great. Another way, we can just make the triple bond over here. Then the nitrogen again gets a positive. You can put 1 H over here. And then we can even put 2 H's here and give that one a negative charge. And then 2 H's in the middle. So that one's okay too. Another one you could have done was just the same thing here. You make the triple bond, get the positive. We put the little lone pair there, negative, and then you can fill it up with the H's. So we're applying the same logic as last time. We just put our triple bonds in 3 different spots, over here, here, and here. You can think of so many other answers that will also end up being correct. So I could have made a triple bond at the very end, have the nitrogen, have the carbon, and then have this H. You can have 2 H's on this, and then 2 H's on your carbon, just like that. And this would technically still be right, because the nitrogen gets a positive and the carbon gets a negative. So you can think of many different ways. You can do them with triple bonds too if you really want to. There's so many different possibilities here. So I'm sure a bunch of the answers are correct. As long as you have something along these lines, you're fine. Okay. Moving on to the next question. This question is a typical isomer question. They want us to make as many isomers as we can with C4H10O formula. So again, before I start, I would like to, and they also want us to name it using functional group nomenclature. Okay, that's a little annoying, but we could do it. So if the formula is C4H10, we go 2 times 4 plus 2 minus 10 divided by 2. So I get 4 times 2 is 8, 9, 10. 10 minus 10 is 0. So total degrees of unsaturation is 0. So all that tells me is that you cannot have any double bonds, you can't have any cyclic structures, it has to be a plain old alkane. So if I have an oxygen like that, do you know of any functional groups where you have an oxygen in the formula, but then no double bonds? Because usually you see O's like this, which is part of a double bond, like an aldehyde, a ketone, or a carboxylic acid. There's 2 functional groups I can think of that are just alkanes, but no double bonds, and those are just alcohols and then ethers. So when I'm doing this question, I have to try to think of making these 2, we have to make structures that have these 2 things. So one of the most basic structures I can make is just alkyl alcohol at the end like that. And if we're naming them by functional group nomenclature, this should be called butyl alcohol. Again, this is not IUPAC. IUPAC would be like 1-butanol. We're not talking about that. They wanted functional group nomenclature, so that would be butyl alcohol. Again, we want to go really systematically, so let's just move the alcohol once more like this. And now, by the way, this name butyl alcohol because this entire thing is a butyl. Now this thing is also a butyl, but it's very specific. This is a sec butyl. So you can write S-butyl, or you can write the whole sec butyl alcohol. Moving on. I know I can't do this now because this is also considered a sec butyl alcohol. So instead of doing that, I have to cut down another methyl and then put it in the middle. So now I can start again. Let's put the alcohol on the top or something. Here we just made isobutyl alcohol. Alright, another one would be if I put it in the middle like this. Well, this would be tert butyl alcohol. And at this point, we already reduced our thing too much. Like I can't break any more carbons to make this even smaller. So I think we have exhausted the alcohol options, and then we have to go into the ether options. So for our basic ether, we can make our little thing, and then we'll split it into 3 and 1 like that. So if you split into 3 and 1 right now, this thing would be considered methyl propyl ether, because you have a methyl, you have a propyl, and an ether. So methyl propyl ether. Okay. Again, this was a split of 3 to 1, so we can do another 3 to 1, and that would be like this. So this one is also 3 to 1, but this one would be named as isopropyl methyl ether. Those are my two things. So again, this was also a 3 to 1. So another one we can do is a 2 to 1. So a 2 to 2, sorry, because we have total of 4. So this is a 2 and 2. And this one just be a diethyl ether. So just remember, for any isomer questions, you want to be systematic. You want to do your degrees of unsaturation to figure out what kind of functional groups are allowed. And then use those functional groups to guide you to type of question or type of answers you can draw. As for the naming, there's no help I can really do here. You just gotta know it. So, okay. Next question is as to using the Newman projections, draw 2 staggered conformations of propyl iodide with carbon 1 in front. So we know propyl iodide will look like this, just like that. And if carbon 1 is in front, then carbon 2 is in the back. So I'm looking at it something like this. So in the front carbon here, I should have a iodide on that one, and on carbon 2 I should have a methyl pointing somewhere. So we have learned from exam 1 that you can have one conformation like this. So if this is 1, this is 2. By the way, they want us to draw a staggered conformation. Just remember, staggered and eclipsed were the 2 opposing sides. Staggered just meant that every single thing was 60 apart, and eclipsed was less than 60 or more than 60 apart. Mainly less than 60 apart, because if you're decreasing this size, then this is getting bigger. So, but both of these are already in staggered form. So the 2 forms we can make are anti and gauche. So this one is putting an I, and then on carbon 2 we'll make our methyl, and this would be my gauche, and this one over here would be my anti. Now I could make the other gauche, but that's the same thing as this one, so we're not gonna make that because we're trying to make 2 different ones here. So those are my 2 different options. And then they say the enthalpy difference between these two conformations is 1 kilojoules per mole. Okay, so they're pretty much just telling us there that the Gauss-butane interaction here between an I and a CH3. So there's nothing here because they're completely far away from each other. There's nothing for the anti. This is 0 kilojoules per mole because we know they're completely anti. But they're telling us that the difference is 1 kilojoules per mole, and we know that this is the Gauss interaction. So pretty much this interaction is 1 kilojoules per mole. So if you ever have a Gauss between an I and a CH3. So, okay, they say using this information for the use this information for the following calculations. You must show your work. Okay, the first question says calculate the enthalpy difference between cis and trans 4-tert-butyl cyclohexyl-iodide. Okay, well, if I make that out, this is my little cyclohexane. Alright, so we have 1 and 4. On 4 I have a tert-butyl, so let's try to make them trans, but let's make the best one here. So if this is pointing down, on carbon 1 the iodide has to point up. So this would be my trans answer. Okay, and then the other answer would be the cis answer. I'm just making the best ones here. The other answer would be a cis answer. Again, I'm going to try to make the best one. If this is pointing down, the iodide on the other question, or on the one spot, has to also point down. The reason why I'm drawing the best answer here and not the worst one is because I don't know the energy of tert-butyl being in the axial spot. So what we learned was if a substituent was in the equatorial spot, that it has 0 kilojoules of energy. It's not really interacting with anything. So here this tert-butanol isn't interacting with anything, and this I is also not interacting with anything. So this thing as a general is just 0 kilojoules per mole. Okay, and then this one here, this one is not interacting with anything, but the I has 2 interactions, and those interactions are I, carbon, carbon, and carbon, right? We know that from before because this interaction right here was I, carbon, carbon in the back, and then carbon. So I know over here was 1 Gauss interaction. On my cyclohexane, I already have 1, and the other one would be I, carbon, carbon, carbon. So we have total of 2 interactions. The way I taught this was you can just count to 4, and I think it's much easier to just do that. So this is just 1, 2, 3, 4, and then also 1, 2, 3, and 4. So you're interacting with that carbon and that carbon. So since there's 2 interactions here and each one's worth 1, this is total of 2 kilojoules per mole. So the difference between 2 and 0 is just 2, so total delta H would be 2 kilojoules per mole. Great. Alright, next question. Calculate the enthalpy between the 2 chair conformations of trans 3-methyl-cyclohexane, blah, blah, blah. Okay, so I can make a best answer here and I can make a worst answer here. So let's make the best answer here. So out of these 2, the methyl is the big bad guy. So we're going to take the methyl and we're going to stick it in the, if we're trying to make the best thing, we're going to take the methyl and we're going to stick it in the equatorial spot. So if on carbon 3 the methyl is pointing in equatorial up, I know on carbon 1 the iodide has to point down because they're trans to it. So this is what I would have. The other option, now I'm trying to make the worst answer, and the worst answer is if the big bad guy goes axial spot. So now the methyl's pointing in axial. So on carbon 1, axial down. On carbon 1, the iodide is trans to it, so it has to point up, which is equatorial. Like that. Over here, the iodine is interacting with 2 carbons, and those 2 carbons are here and here. So this, we already know the energy for. This is the same as the last question. So this is the energy of 2 kilojoules per mole. But when a methyl is in axial spot, it's interacting with this. So, and the other one is 1, 2, 3, and 4. So there's those two interactions. And this is a number you kind of have to memorize. If a methyl is interacting, it's 4 kilojoules per mole. This is just something we have memorized. Your teacher can be nice and just give you this number, which I kind of expect them to do. So since we have 2 of those, the total here would be times 2, and we end up getting 8. So the difference between them would be 8 minus the 2 from here. So the difference will end up giving me 6 kilojoules per mole. Just like that. Next question says to calculate the difference between trans, 2-methyl, and iodine. Okay, so same thing, we got to make a best and the worst here again. So we're going to do the same old thing. So if we're making the best again, we look at the bad guy, we say that's the methyl. So let's just stick in the equatorial spot. If I'm making this trans and the methyl is pointing down, then on carbon 1, the iodine has to point up, which happens to be also equatorial. Right now, this interaction is iodine, carbon, carbon, carbon. Again, that's the interaction just right here. That's iodine, carbon, carbon, carbon. And we know that interaction is worth 1 kilojoules per mole. So this is 1 kilojoules per mole. If we make the worst interaction, well, the worst one is we take the methyl, we stick it in the axial spot. It's right now pointing up. So on carbon 1, iodine has to point down, which is looking like this. So here you have the carbon interacting with 2 other carbons on top because it's an axial spot. So that's total of 8 from before. We worked that out right here. And then the iodine being in axial spot is also interacting with 2 things, and those 2 things are here and here because that's 4 away. 1, 2, 3, 4, and 3, 4. And I know each one of those was 1, and then we worked that out over here. That was total of 2. So 8 plus 2, I'm getting 10 kilojoules per mole for the second structure. So the difference between the 2 will be 10 minus 1. So I get total of 9 kilojoules per mole for this answer. Great. So if you don't understand that, come to one of the review sessions and we can work on this and you can ask me more specific questions. Okay, moving on. Using the templates below, you may not need all of them. Okay, that's annoying. To draw the structures of the non-chiral methyl cyclohexyl iodides. Okay, so I just have a methyl and an iodine on my thing. Be sure to show stereochemistry. Okay, since a methyl and iodine are 2 different things, I can't really make meso compounds. If they were both methyl, then you can make meso compounds, but right now we can't. So if I'm trying to make non-chiral stuff, then I can just say something like this. Let's say if both of them were I and CH3, well, if they were both here, like that, well, that's not even considered a chiral center because that's not 4 different things. This side and this side is the same. So that's not even a chiral center. This is non-chiral. Another way would be, let's say you had a I here and then a CH3 here. Let's say they were both wedge or cis. Well, again, they have not the same. Like if we look at this carbon, it has a iodine, it has a hydrogen, and then it has all that stuff and all that stuff. So it's both same on both sides. So this one is also not chiral. So this one wouldn't be counted as chiral. And another one would be if they were trans to each other like this. Same thing, the carbons aren't even considered chiral because you don't have 4 different things. So those are the only 3 you can think of. There is none here. The reason why I didn't make wedged and dashed here, because they're the same thing. So here, this is all cis, this is a trans. But here, you would have to make them opposite to each other. So like you can show it like this, but that's the same thing as if I showed the dashed one as wedged and the wedged one as dashed. So same old thing. Okay, moving on to the next question. For each of the following pairs of structures, use the given abbreviations to indicate whether they are identical, enantiomers, or diastereomers. This is where you have to work out your RNS and hopefully get the answers. So let's start with the first question. Okay, we can see in the first question that every single spot is switching. This was dashed and then it went to wedged. This one was wedged and it went into dashed. This one is wedged and it went into dashed. So the only time we see that is if you're enantiomers. Because what do enantiomers look like? If this was R, then this one was considered S, if you flip on a side. So if you're going to switch on every single chiral carbon, well, then you're enantiomers. That's enantiomers. Notice the next one is doing the same exact thing. This was dashed here and then it went to wedged. This one was wedged here and it went to dashed. So it switched at the exact spots. And like the entire skeleton looks the same. So because it did that, if you work it out, it'll again be enantiomers. If you want to, you can totally work it out. So this is your fluorine, that gets a 1, this gets a 2, and this gets a 3. So this is right now looking like R, but then since the H is in the front, you actually flip the answer, and this is actually S. Well then, the other side will be R. So they're enantiomers. The next one's a trick, because the base skeleton is going up, down, but here now you're going down, up. So the way I do this question is I kind of just take this molecule and I flip it. But if you don't like that, you can work out R and S. So if I do R and S here, I would get 1, 2, 3. Right now that's R, and I don't need to flip the answer. So this is R. And for bottom one, I get also 1, 2, 3. So this one is also R. If I do the other side, right here, I get 1, 2, 3. This is right now S, but I need to flip the answer because H is in the front. So this one is R. The other one is 1, 2, 3. Again, it looks like S, but you need to flip the answer, so it's R. And as you can see, I have the same thing. So this is indeed actually identical. Cool. All right, next question. Next question we get, you can do R and S again. Well, I get 1, 2, 3. This one is R. And this one is 1, 2, 3. This one is S. So one is RS. The other one is 1, 2, 3. This one is S. And then this one is 1, 2, 3. This one is looking like S, but it's actually R. So wait, it's looking like S, but it's actually R. Did I mess this up? Let me see. That's R, that's S. This one is R. No, this one's R, I'm sorry. This one should have been 1, 2, 3. This is R. You don't need to flip it. It stays R. So this was supposed to be R. And this one is 1, 2, and then 3. So this one is S, but you need to flip it to R. So you actually end up getting R, S, R, R. And if you ever get 3 of the same like that, well, those are diastereomers like that. The next question, you can again just do R and S. I think that's the easiest way to do it. But first, we're in a Newman projection, so we have to make it into a line diagram. I don't know if you know how to do R and S from Newman. If you do, then great, but I'm going to just draw it out. So I'm going to draw this molecule out if I was looking at it from this side, like that. If I draw that out, I'll get this. The CH3 is in the front. So this is that CH3, and this CH3 is in the back, so this is that CH3. I'm going to do the same thing for this one. I'm going to look at the molecule this way, so I end up getting this, and then both of the OHs are in the front, like that. Okay, so if we do R and S here now, it ends up looking like this. I would get 1, 2, 3. So this is looking like R, but then the H is in the front. So this is actually S. This one I get 1, 2, 3. This one is R. And the H is in the back, so it's already good. So this one is R. If I work the other one, I get 1, 2, 3. This one is just S. And this one I get 1, 2, 3. I also get another S. So when we work it out, I have S, R, S, S. So that's 3 of the same things again. These are diastereomers. The next one, this is not a chiral center. So since that's not a chiral center, this thing isn't even chiral, and these are actually identical compounds. Now, this last thing, I'm not sure that you have learned this, but what we're doing here is, if you do E and Z here, well, out of these two things, what gets the priority? Well, this gets the priority, the methyl. Out of these two, methyl and all that, well, all that gets the priority. So I know this double bond is Z. And if I look at the other double bond, well, this one is technically cis, but we're going to also just call it Z. For this one, let's call this one E because they're opposite to each other. And the other one, this one will end up being Z. So just like we do with R and S, if you get this with double bonds, it's the same principle. So I got Z, Z, E, Z. That's 3 of the same things. And these are actually considered diastereomers. So if you didn't learn that, I wouldn't worry about it too much. But if you think it's important, then great. This is how you do it. All right, moving on to the next question. This was a question that you recently had on your test. But this one is just a little bit different. So normally you're given a molecule and they're like, okay, well, show us the different types of products where the chlorine can go. And they tell you the ratio for the chlorine going to the tertiary spot or the primary spot or the secondary spot. What we're doing differently in this question is that I'm telling you the percentages for the answers. I'm telling you the actual yield. But what they're asking for is what the actual selectivity was. So normally we used to have like 5 to 4 to 1. But like they're asking for what kind of selectivity we have here. So if you think this is a type of question that your teacher is willing to ask, then great. If not, the question's not going to change much for you guys. You got to just draw the different kinds of products and then just calculate it normally. But again, we're trying to find the ratio here. And we already have the percent yield. So if you want to know how to do it, well, this is how you would do it. The thing is, for primary, it never changes. The selectivity for primary will always be 1. So if you want to do this question, what you have to do is you have to find the primary answer, which just happens to be this one. Once you find your primary answer, you have to remember how you did the calculation. The way we did the calculation was we said, hey, this primary has 1, 2, 3, 4. So there's a total of 12 spots I could have taken. And then we multiplied it with that number, that ratio number. And then we got a number. And then we took that and then we divided that with the total number we had. So we know the ratio number for primary is 1, but the total number is the thing that I don't know. So if you remember, like you just times it with everything, you add all the numbers up and then you divide that number by everything. So we're trying to figure out what that total number is. So if you do 12 times 1 divided by that total number, well, that gives me a percentage. And that percentage happens to be 24 divided by 100, just like that. So if we have this question and we work out the answer for x, well, I get 1200 equals 24x. So x equals 1200 divided by 24. So normally you would have to do this math. I don't think you probably have to. So let's just put it in a calculator. I end up getting 50. Okay. So we know that total number now is 50. So now I can just go through one of the answers and then plug in 50 for the answer. So let's say we look at the tertiary answer. Well, I know tertiary, there's only 1 spot and 2 spots. So there's 2 spots. What I don't know is the ratio number, but I do know that the total number is 50 equals the percentage I'm getting is 28 divided by 100. So this will end up giving me 200x equals 28 times 50. So if you end up doing, here, let's move this here. So if you keep going with this, the x is gonna end up being 28 times 50 divided by 200, or 4. So 28 divided by 4, well, this 2, 1, 4, and this is 7. So you could put it on the calculator. I just ended up doing the math, but you should end up getting 7. So selectivity for a tertiary spot happens to be 7. And then the last one we have is secondary. Again, you do the same thing. I know for this specific secondary spot, there's 2 h's that could have replaced. I don't know the ratio for it, but I do know that the total is 50. All that's giving me is 16 divided by 100. So I end up getting, again, 200 equals, well, 200x equals 50 times 16. So x equals 50 times 16 divided by 200. I cancel these zeros. 5 goes into 24. 4 goes into 16 by 4. Just like that. So this is how you would find the ratio. Now, again, I don't know how, like, the likelihood of them asking you a question like this. I could have just given you a question where it was like normal and you've seen it before, but I feel like we've done enough of those, so I think this one is more helpful, just in case they throw you an off ball where you have to figure it out. So, alright, that's how you do that question. Let's move on. The next question we have is just a bunch of reactions. So OSO4 adds 2 cis diols or alcohols. So let's do that. So let's say they both go in wedged, just like that. The other answer would have been if they both came in dashed. So since this didn't change, if you remember correctly, well, that makes diastereomer. So let's say for some reason this was like R and this one was S. Well, this one is, let's say, S. In the other answer, that one will stay S, but these ones will change. So that tends to make diastereomers, if you want to write that down. This one we have to add BRs. They have to be trans to each other. Again, this methyl isn't being changed, so we will make diastereomers again. So you can get this answer, and the other answer would be if they went in like this. Again, these two things are diastereomers of each other because this methyl didn't switch stereochem. So that would be the other answer. These are also diastereomers. Ozonolysis, we're just going to cut through the entire thing. So this one might be weird for you. If you have more than one double bond, you're going to cut through everything. So what you're just getting is 2 of these things. We're just cutting through the entire thing like that. The second part is DMS, so we don't have to make carboxylic acids, and there's no diastereomers thing here. Next one, HBrROR. Well, that one I know adds cis, H, and a Br, but anti-Markovnikov style. So my answer should be, let's say they both go in as wedged, well then the Br will go in wedged. You will push the methyl to the back, and then the H will go in wedged like that. So I would get this answer, and the other answer would have been if they went in as dashed. Well, if they went in as dashed, this would be my H, this would be my methyl, and this would be my Br. So here we ended up making, what is this? This is S. This is just S and R. Alright, let's work it out. So I would get 1, 2, 3. This spot is S. And this spot is 1, 2, 3, R, but S. So this spot is also S. Here this would be R, and this would be R. So you end up making enantiomers. Alright, next question. NBS just adds a Br on the allylic spot. So my allylic spots are here, here, and here. That's just one away from the double bond. And out of those 3, the one that's most substituted is that one, so we're going to put the BR there. Now the BR can again come in as a wedged or a dashed. So let's say it came in as a wedged, well then my answer would be that. And the other answer would be the enantiomer if they came in as a dashed. BH3 THF, this question was to add a H and a H and a OH, but the OH going anti. The H and the OH have to go syn to each other. But notice this one again, there's a wedged methyl there, which is going to stay there. So we're going to make diastereomers already. I already know that. And let's say my OH went in wedged. Well, then it would have went in like that, which would... So I put the H and the OH, syn addition, both wedged, and then this would be my methyl. And the other answer would have been if they both came in as dashed. So if this was the H, this was the OH, this methyl doesn't get switched, and this is your CH3. Those would be the two answers. So this should be really not so bad because we just had exam 3, so I hope that was alright. Alright, next question is your first mechanism question. Just looking at it, I can see that this was a ring expansion with HBr. So the way this looks like is something like this. The double bond's going to attack the hydrogen to make the carbocation. This part is reversible, and you end up making this plus Br minus. At this point, you can do your ring expansion. So this bond is going to open up like that. This is not reversible, and you end up making a cyclopentane with the positive over here. Actually, the positive is on top, but it doesn't really matter. The next one, you look to your left and your right, and you know you can do a hydrogen shift. So we're gonna pick up this hydrogen, and we're gonna move it there, and then that's gonna end up giving us this thing. And the last step is where the Br can come in, and they didn't show the Br coming in wedged or dash, so I guess it doesn't matter. So if the question was this, it would just attack there, and that makes my answer. So if we work out the reaction coordinate diagram, since I have 4 steps here, I should have 4 bumps. The first bump being the biggest bump. So originally I was good, and I went to something really bad. The ring expansion should release some energy. This should release some energy. And then this one should be the last one. But total of 4 peaks. So I should get something like this. You start off bad, you go really high, you lose a little bit energy, it's better, 2, 3, and then 4, you end up being better than original. As long as you have the 4 peaks, you should be fine. Make the first peak the highest, and then we're good. Next question. How long is this? Oh my god, this is really long. Okay, next question. Write the structural formula for each compound. Use wedges and dashes as appropriate. Okay, so here they want us to make S2-methyl 3-pentane thiol. Okay, so my main thing is a pentane thiol. So let's make a pentane, which is like that. On 3, I have a thiol. So 3, I have a thiol, like that. And on 2, I have a methyl, so like that. So I have to make this S. So I know this is not a chiral center because these are both methyls. So the S would have to be where the thiol is. If we're doing RNS here, I would get 1, 2, 3. Right now, this is going S. So if I want the S answer, all I have to do is I have to make the SH as a wedged. And that would be my answer. Next one. Give the IUPAC name for the following compound. Okay. Right off the bat, the very first thing I can see is that I have wedged and dashed. So I should probably do my RNS. So if we do the 1, 2, 3, 4, the alcohol gets the smallest number possible. Well, this gets a 1, and then this would be my 3. So if I was to work out just the name itself, that would be a 3-methyl. And then you could do 2. Actually, you don't have to do one cyclohexanol, because in a cyclic compound, alcohol is already, it's like everyone already understands that this gets number one priority. So you just have to write 3-methyl cyclohexanol like that. Now all you have to do is the R and S. So I know on carbon number 1, I will get 1, 2, 3. So that right now is going counterclockwise, which is S. So I would get 1S, and then 3 is my, I would get 1, 2, 3. This is R, but actually S. So this is going clockwise, but you actually flip it because the H is in the front. So this one is also S. So final answer would be this thing. 1S, 3S, 3-methyl cyclohexanol. Next one. Again, I don't know if you know how to like name methoxy and ethoxy. But if you do, the main chain right here is actually considered to be this thing. That's just a butane. So I have a 2-butanol. So I would kind of go on 4. So this is considered my 2. This is considered my 4. So you go 4 ethoxy, T ethoxy, 2 methyl. So this is 4 ethoxy, 2 methyl, and then you can do 2 butanol, or you can do but 2 and all, whatever. So we'll just do 2 butanol like that. I don't know how crazy they're gonna be about this, so that's why I put a little question mark next to it. Alright, next question says to circle the compound with the highest boiling point. This one's not so bad. It's just whichever one has hydrogen bonding. So you just have to remember hydrogen just wants to have FO and FON. So if you're connected to the fluorine, oxygen, or nitrogen, that's the best one. So this one has hydrogen bonding, thereby it has higher boiling point. Which one has higher water solubility? Again, you need hydrogen bonding. If you have more hydrogen bonding, the better it is. So it's the second one. Next question is, they want a mechanism where you convert the enol that looks like this. They want you to convert that to your aldehyde like that. So we have it in sodium hydroxide, which is NaOH. So this is in base, and I went over this. The way we're going to show this is like this. The OH grabs the H, this goes here. This part is completely reversible. So I end up making O minus plus water. And then second step would be to protonate. So we have water. So this goes down, and then this grabs the H from the water. So here, let me make it out for you. Alright, it's water like that, and then this ends up giving me my aldehyde plus OH minus is reformed. Awesome. Next question. This question's asking for the mechanism for this reaction. We can see this is alcohol elimination, which happens in acid, water, and heat. So in this one, the first step would be to protonate. So if you have H2SO4 as your thing, we're going to use it like this. So you're going to protonate to make it actually a good leaving group. This is just a hydrogen transfer, so this turns into OH2 and plus. So you make HSO4 minus. Okay, now my OH2 is a good leaving group. This is happening on a secondary, so you have to remember a rule. If you're a secondary alcohol or a tertiary alcohol, this is supposed to be E1 reaction, not E2. So at this point, the water will just leave and you form a carbocation. So the water will just leave. It's not reversible anymore. And then you form a positive there. Once you get the positive, you can look for rearrangement, which is exactly what happens. So this H is going to get up and move here. you end up getting a positive over here, and the H moved here. And then the last step is where you have to do the elimination. So another water will take this H, and then this will go here to give your final answer, which is the double bond plus H3O plus, just like that. Awesome. Next question is a synthesis question. Looking at this, all we did was this structure staying the same. All we did was we created a ketone right here. You can also do the same thing where the ketone is over here. That's like pretty much the same thing. So this is a simple old alkane in the beginning. So I know the only thing I can do to an alkane is Br2 light. So if I do Br2 light, the Br goes on the more substituted spot, just like that. Now I want the ketone to go over here at the end. So somehow I have to, so you have to ask yourself, well, how do you make ketones? If I ask myself that, the answer you should get is like, well, it can be an alcohol. And then you're like, well, how do you get alcohol? And since this is sitting at like the less substituted spot, okay, the way you can get alcohol is there's multiple ways you can do substitution, but you also have your double bond reaction. So that's the reaction they want you to do. So what we're doing is we're taking this thing and we're gonna put it through E2 reaction. So like NaOCH3 with HOCH3, and that's gonna eliminate. That's gonna make a Zeitz-Steph answer. So you can go over here or here, but those are same products, so it doesn't matter. Once you get that, I want an OH to go on the less substituted side. So that's hydroboration. BH3THF, H2O2, water, and then like NaOH. That will make this. And at this point, you can just do PCC. PCC, Swern, DMP, all that stuff. If you had any other way, feel free to, like email me to ask me how you did it. And I'll let you know if you did it right. Okay, next question. Another just box question. This is making one of those weird, and this is like one of those weird reactions, if you remember. This one involves the carbene. So the one that forms CCl2, well, that one was CHCl3, and then you have TBUO, Na, or K. Those are the reagents. This one is, you can, if you take an epoxide and you put it through a reducer, it just reduces it going to something like this. So there's two spots, there's that spot and that spot. The alcohol ends up going on the more substituted spot. The other spot just gets like a H. So you would end up getting that. This might be a reaction you haven't learned though, so I'm not really sure. Put little question marks next to it. The next one, again, I don't think you've learned this reaction, but right now my structure looks like this. So this is the less substituted side, that's the more substituted side. If you have NH2 just like that, well, that's considered basic conditions because that's not an acid right now. This just looks like this. That's not acid, so we're going to consider that as a basic condition. And if you remember Blam says to attack the less substituted side, so we're going to attack over here. We're going to attack the less substituted side, and this will open up like that. So your answer should be, you attack over here, CH3. Since you attack here, you're going to have two H's here, and then this will be your O minus. And once that happens, this O minus kind of grabs this H. So I seriously don't know if you've learned this reaction yet. But if you think it's important, then great. We end up making that. Just remember, base attacks less substituted side, acid is more, And then you should be alright for these types of questions. Alright, moving on to more questions. So alcohol with HBr, well, HBr is just an acid, so you're going to just grab that H first. So once you grab that H, you're going to make OH2 plus. This is a secondary spot. In a secondary spot, water just leaves. So once that water leaves, you get a positive, you look for rearrangement, and then you end up making this. Once you get that, at that point, the Br minus can just attack at that spot. So once that attacks, that's how you get this answer. Here, I'll draw it just like it's drawn there. Whoop, whoop, whoop. Like that. So this was just substitution. It just happens to be SN1 because it was secondary. Another one of those weird reactions that uses a carbene. Look at the ending product. This is trans to each other. So all that means is your double bond needs to be trans at the beginning. Just remember this reaction requires a double bond. So we're going to have something like this. Like that. So if you put this through ZnCu and CH2I2, kind of goes like that. It gets rid of the double bond. So instead of making these trans, they're kind of just making it as wedged and dashed. So you have that double bond. Tosyl chloride. Remember, this reaction does not flip the stereochemistry, it retains it. So if you're doing just the first part, you're turning your alcohol part into a dashed OTS, which acts just like a Br. At this point, they're doing NaCN, so the NaCN will make it actually rotate. So you're going to flip the stereochemistry now, because the second part is SN2, and this is going to end up making a wedged CN. So you go retain, and then you flip. Next one, PBr3 flips and NaSH also flips. So here what we're doing is we're going to first flip to wedged Br, and then you do NaSH, which is another flip. So they are both SN2 and another SN2. If you do that, the final answer would be a dashed SH. Okay, finally we're at the multiple choice, and then we're done. The first multiple choice says, how many of the following molecules have a dipole moment of 0? Okay, so dichloromethane looks like this, CH, H, Cl, Cl. So I know one of these is wedged and the other one is not, but this clearly has a dipole. It's going in a certain direction, so it's not this one. This one does have a dipole. Chloroform, that's CCl4. So if all of these were Cls, well, yes, that doesn't have a dipole like that. So this is one of your answers. Carbon tetrachloride, same thing. Actually, I think chloroform was CHCl3. This one might be CHCl3, which does have a dipole. Yeah, let me check. Let me check. Yeah, so chloroform is CHCl3. If it's CHCl3, it would actually have a dipole going that way. So this one is actually not one of the answers. But carbon tetrachloride would have it. Would not have a dipole. So that's your first one. Next one, cis 1,2-dichloro ethylene. So like that. This one also has a dipole. You're going this way. Then you have trans of the same thing. Well, that one doesn't have a dipole. Everything cancels out. So this is another one. And then carbon dioxide looks like this. You're not moving in this one either, so this one also doesn't have a dipole. So in the end, you have 3 of them that don't have a dipole or have a dipole of 0. So the answer would be 3, and those are the circled ones. For this one, the number of unhybridized valence shell p orbitals Ooh, okay. The unhybridized will be, well, this is sp2, so that's 1. This is sp2, so that's another one. This is sp2, so that's another one. That's 3 total right now, plus any of the hydrogens, and the hydrogens end up being 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10. So I get 13. That's not one of the answers. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This one, the number of unhybridized valence shell p orbitals. Oh, p orbitals. Oh, this should, for you guys, this should just be 3. Don't think about this one. This is sp2 and that's supposed to be 1. This is sp2, that's also supposed to be 1. What they want you to do is they want you to think this as 4 and this as 4, but that's not how like you learned it. So oh no, actually they want you to think that one as 4 and that one as 4, but you didn't learn that way. That was just a stupid Boykus rule, so don't think of that one. The spots that I'm showing you, these are the only spots that are sp2, and if you're looking at p orbitals, each one of those has 1 unhybridized, so you should have a total answer of 4. This is not right. This is the old stupid rule we used to have. The answer here should be 4. I don't know why I wrote 3 here. This was 4. Just like that. So ignore that. Rank the following acids in order of increasing acid strength, weakest one first. So you have acetic acid, which looks like this. Then you have trichloroacetic acid. That one will look like this. Then you have hydrobromic acid, methanol, and then 2-chloroethylamine. Okay, so I have this. Just off the bat, I know one of the best acids is HBr, so I'm going to try to pick 3 with being the last thing. So I know this one has 2 as the last thing, 2 as the last thing, 2 as the last thing. Okay, wow, the answer is A. You don't even have to do it. HBr is supposed to be the best acid here because that's the only one that's connected to a Br. That was really straightforward, actually. The next best one should be the one with the carboxylic acid, but with Cl's also pulling on it, so it should be 2, and then it should be carboxylic acid, the normal one, and then you have your methanol, and the nitrogens are the worst ones, so because they're actually more basic. Wow, that was really straightforward. As long as you knew HBr is the best acid, you're good to go there. The next question is your enantiomeric axis question. They're telling us here that the mixture has the rotation of 20, and then the pure R turns in -40. So I have S, I have R, and I have to know what I have more of. So the R is turning in the -40 direction, so the S will normally turn +40. My mixture is turning in the positive, so I have more of S. So then you do EE equals observed over pure. The observed is 20 over pure is 40 times 100. Cut this out, 4 goes to 4, and I get 40. This is how much extra S I have. This leaves me with 60 that I'm going to split evenly. So 30 goes to S and 30 goes to R. I add my 40 extra, which ends up going to be 40, 50, 60, 70. So I have a total of 70% S and 30% R. Is that an option? Wow, that's not an option. 30, did I miss anything? Oh, it's 4 times 5 is 20. What the hell's wrong with me? Okay, it's 5. This should be 50. And then I should be left with 50. Bad math. Then I have 25, 25 each here. And the answer should be 50, 60. So 75% S, 25% R. That's C. Sorry about that. Horrible math. 20 divided by 4 is 5, not 4. Okay. Next question's asking me, how many of the following species are electrophiles? Just remember, electrophile is anything with a positive, usually, that doesn't have an octet, and stuff can attack it. So, doesn't have an octet, only has 6 around it. Doesn't have an octet, only has 6 around it. Doesn't have an octet, only has 6 around it. No charge, nothing, so this is perfectly fine. This is actually a nucleophile. The OH part can attack. And this thing actually does have a full octet because there's 3 H's there. So this is actually not an electrophile. Even though it has a positive, that doesn't count. There's actually only 3 of them. The answer is B. The ones I circled. Next one. How many products do you expect to be formed in the allylic bromination of 1-methylcyclohexane? Count all stereoisomers separately. Okay. So I would get, let me think about this. Get 1, 2, count all stereoisomers. So I would get 1, 2, 3, 4. Oh, this is a reaction. This is something you haven't learned yet. You never discussed this. Don't worry about this. You don't have to worry about this. This is another thing you never learned. You never learned IR, so don't worry about that. Next question says to figure out which of the reactions will give you a meso. The first one is you're starting with a trans 3-hexene, and then you're doing Br2. So I would end up making a wedged Br and a dashed Br. This is 1, 2, 3. So this is S. This one's 1, 2, 3, and this one's R. So SR, same substituent, same everything. So this is a meso. The cis version is not going to give me the same thing because the cis is going to end up giving me the same here. Cis is going to end up giving me something like that. So I'm going to get S and then S. So those are enantiomers, so that's not going to count. The next one is a cyclohexene that goes through H2PT. That's not even a chiral center, so that's not considered meso. The next one is another trans 3-hexene with OSO4. So another trans 3-hexene. You go OSO4, that adds 2 cis OHs, so I get that. Well, this one is going S, this one's going S. But if it's cis, that one will work. So you should have 1 and 5. The answer should be C, to my belief. Next one. You have not learned this reaction because you don't know how to add carbons. Don't worry about it. Next one, SCH3, there's an Na there, so this is just plus and a negative. I have an epoxide and I have a basic thing. So according to BLAM, you attack the less substituted side. There's these 2 spots and the less substituted spot is right there. So the final answer should be you attacking that spot. If you attack that spot, this CH3 will be dashed, this OH will end up going wedged, and then the SCH3 has to come in as a dashed because it's a backside attack. You just have to attack the less substituted side, and the answer is A. Next one, they're trying to figure out which one has the best boiling point. Well, the one that has the best boiling point would be the one with the most hydrogen bonding, which is there. The next one would be this, so this one would be first, this one would be second. Oh, they want the lowest boiling point first, so we're going to call this one 5, this one is 4. Okay, 4 should be at the end, so that can't be this, and it can't be this. After that you have 5, so the only difference is 1 better, or is 2 better? Now if you don't know this, this one still has an oxygen, so this one is better than if you didn't even have that. So this one should have the lowest boiling point, and this one should have a little bit higher because it at least has the oxygen. So it should be E. 2 should be the worst, then it should be 1. This one has 2 oxygens. This one has the oxygen and the hydrogens, and 2 of them, and this one has like 1. So final answer 21354. Last question. Yay. Select the best reaction conditions to carry out the transformation shown below. As we can see, this OH turned into an aldehyde, so that was oxidation. If you did H2CrO4, that will make it into carboxylic, so that's not what I want. Concentrated H2SO4 does nothing there. Okay. COCl2 DMSO NET3, that's Swern, and that's a mild oxidizer. That would be my answer. HiO4 only works on diols that are 1 and 2 to each other. And MCPBA CH2Cl2 is a double bond reaction. So the answer is C. What color is my exam? White. So the answer is B. What the? Why is it going B? That's confusing. Okay. Well, that's it. We're done with the super long test. That took forever. If you have any questions about anything, feel free to, email me or whatever. And I will wish you best of luck for your tests. I will try to do another one of these exams. I'll try to make them into another packet and then make another video out of it, hopefully tomorrow. And then depending on how many people actually watch it, I might do like a third one. I don't know. We'll see. So all the best on your finals. Let me know if you have any questions. Thank you.